Have you ever seen weird boards like these ones before? These oddly textured boards and panels are used to assist and encourage the diffusion of sound energy within the space that they're equipped in. Diffusion is absolutely critical for obtaining a balanced yet lively sounding room for recording or mixing, or even mastering as well. But what is diffusion anyway? Well, generally, diffusion is the flow of anything, meaning light, heat, molecules, people, ideas, money, anything, from an area of high concentration to an area of low concentration. You're familiar with several examples of this already, like the heat diffusion or molecular diffusion, but you might not know exactly what they are. Sound energy will diffuse on its own without any interference from engineers or architects due to the nature of the medium it travels in, but we can help it along with certain treatments and design practices. But why do we care about having a diffuse sound field anyway? What is it worth as a musician or audio engineer? Well, I'm glad you asked. A diffuse sound field is more spatially uniform and less prone to irregularities and sharp echoes and other artifacts caused by reflections. Essentially, a diffuse sound field is one where the reverberation time is more or less uniform for any place in the room and is independent of frequency. Diffuse sound fields are absolutely essential in spaces where we want to portray a source sound, such as like a band performing or an orchestra performing, to the entire space. So imagine a concert hall. We want to hear the performance as it's intended to be heard by the musicians from every space in the auditorium or the concert hall. And that's a significant engineering and design challenge. The architects and builders involved will have to make carefully calculated decisions about what materials to use and how to geometrically arrange their space to create the most diffuse sound field possible. We don't only care about diffusion in concert halls though, we also really need it in mixing and recording spaces. In mixing spaces, diffusion treatment kind of works in concert with absorption treatment to reduce the impact of reflections on our perception in our mixing space. However, unlike absorption treatment, diffusive treatment does not remove energy from the room. It only spreads it out over a larger area and reduces its perceptibility at any one place. That last point about not removing energy is key for recording spaces, because when we treat a recording space, we don't want the room to sound dead, meaning we don't want it to remove all of the reflective energy from the space, but we want to create a more balanced and less distorted reflection image from all of those. Diffusion treatment is perfect for this use case. All right, so let's grab some of these weird panels and get into it, shall we? So we know that in general, diffusion is a process where things that are highly concentrated move out of their highly concentrated state to areas where they are less concentrated. And like I mentioned, this applies to all sorts of different natural entities and quantities and phenomenon in pretty much every aspect of science or life in general. Two familiar examples of diffusion are thermal and molecular diffusion, and understanding the basics of those will help us have a much better understanding of how diffusion applies to sound. So let's take a look at an example of heat diffusion. Heat flow always follows the temperature gradient from areas of high temperature to low temperature. This is why an ice cube in like a drink that you're drinking will melt over time, because there's heat moving into it from the atmosphere, from your hand, from whatever else, because it's a lower temperature space. So the heat knows that it can move there because it's less concentrated there. Here's a visual example of molecular diffusion. This colored liquid spreads out over time once it's dropped into the bowl of water. And it does this because it's going from a state of high concentration, where it's in the drop, it's just a single drop of all of the same type of molecule, very packed together, and then it enters the larger space of the water, where it can diffuse out and go from its highly concentrated state to a lower concentration. The same thing happens to gases, or different types of gases, when they come into contact, but it's harder to see. But we can still explain this example. So consider like maybe your roommate or someone you live with or just a friend coming into your house with like some hot food that they just picked up. As soon as they walk in, you can probably smell the food that they brought, right? You don't have to walk over and be right next to it to smell it. Well, this is because the gases that actually carry that smell to you are able to diffuse through your room as soon as they enter. If they didn't, you would have to put your nose directly next to something to smell it, but we obviously know that that is not the case. Okay, so we know diffusion is responsible for mixing our drinks and keeping our houses warm. But how does this apply to sound at all? Like I said earlier, diffusion is all about concentration. When things are highly concentrated, their potential energy rises from whatever potential they may be a part of. It's going to rise whenever they are brought closer together. Nature always unfolds in such a way that systems will reduce their potential energy as time moves forward. This is why things fall to the earth in the earth's gravitational potential, or why current flows a certain direction when you place a battery into a circuit. It's all about moving from a high potential state to a low potential state. The thing that is falling has a lot of potential energy from being elevated above the source of the potential, just as the electrons or charge carriers have potential from their separation. Sonically speaking, sound energy will create a pressure wave in the medium, right? Like if we excite a guitar or we start, as I'm talking right now, I'm exciting a pressure wave in the air of this room. Pressure acts on the concentration of molecules in the medium. See where I'm going? When those air particles are pushed together, or they don't have to be air, it could be a fluid, any other fluid. When those particles are pushed together from the pressure wave of, like my voice, for example, their concentration changes, and like I mentioned earlier, their potential energy changes. When that happens, those air particles are going to start taking part in a diffusion process to lower their potential energy. In this case, the air pressure of the sound wave itself is the driving force behind the diffusion. So this slight diffusion of particles as the sound wave propagates actually has an effect on the sound that we hear. So wait a second. If sound energy diffuses on its own, then why do we need to treat our rooms for it? Shouldn't it just take care of itself? The diffusion process driven by our pressure wave happens on a time scale that's too slow to override the motion caused by the sound wave itself. If this wasn't true, then the temperature of air would have a drastic effect on how things sound, because diffusion rates are directly proportional to temperature. Now, temperature does have an effect on the way things sound, but it's very, very small and hard to detect from just our ears alone. So this type of self-driven diffusion from our sound wave isn't really enough to cover the use cases that we mentioned in the beginning of this video. To create a more diffuse sound field, we need to create our own sources of randomness for the sound field to interact with, to take the place of the randomized diffusion process. Sonic energy isn't just diffused by the pressure wave of sound itself. It can also be spread and diffused by the objects it is reflected from. The goal of any piece of diffusive treatment is to lower the energy density of sound that it reflects. As a simple example, we can compare the reflection images of just a flat plane surface to that of a convexly curved surface reflecting the same source material. So here we see the reflection of just the flat surface, right? The incident waves are just pushed straight back to where they came from. So essentially what's happening here on the plane surface is that it's just sending back a time-delayed copy of the same material. This scenario is extremely common for reflections coming from the back wall of a mixing space that then come back to like the back of the engineer's head. It's just sending a time-delayed copy of the source material that can really interfere with the mixer's perception. Now we see the curved surface, right? We have the same sort of incident source material, but when it's reflected, the whole surface is still taking part in the reflection. But because it's curved, then each point on the curve sends its own copy out in another direction. So we take the same energy and just displace it over a larger area, meaning that the perceptibility of that reflection is lower in any space in the room. So another example of this diffusive reflection geometry is a corner. We can take a look at this one as well. We see the sound energy coming in to both sides of this like corner, right? And then each wall making up the corner reflects its own copy out in all sorts of directions. Both the curved surface and the corner surface are much more effective at diffusing sound than the flat surface, which really doesn't diffuse it at all. The corner surface is just slightly more efficient in most cases than the convex surface. So these two examples show the basic principle of any kind of diffusive treatment. The diffuser reflects incident sound energy over a larger area than it would have had it just been a flat plane surface, meaning that reflection has a lower energy density and is thus harder to perceive as coming from a specific place, and instead just adds to the overall ambience and harmonics of the room's reflective image. But there's actually more to it than just this spreading caused by certain geometries. Most diffusers also take advantage of phase effects to further reduce this energy density apart from just what we get by the geometry alone. If you're unfamiliar with the concept of phase or interference, then you might want to check out Scitone episode 1, where I treat those two topics alone and just go into detail on them. Let's take a look at this quadratic diffuser. You can see it's made up of a bunch of troughs in this larger panel space. And if you look closely, you can see that each trough has a different depth. The varying depths here play an absolutely critical role in the diffusion advantage we get from the piece of treatment like this. We can understand their effect by comparing the reflections from this type of setup to the flat plane geometry again. So we already saw with the flat surface that it sends back just like a time-delayed copy of the original signal. To understand the quadratic diffuser, we can imagine each trough, each section of the diffuser as its own plane surface, right? Each one of them is going to be at a different distance away from the source material. As an incident sound approaches this type of diffuser, each one of those troughs, which remember we're imagining as its own plane surface, is going to reflect the signal back towards the source. But here, instead of just sending one big time-delayed copy, we're sending a bunch of different time-delayed copies, each with a different phase. The phase difference comes from their varying depths, right? The source has to travel a different distance to get to each trough, meaning it will have a different phase value when it arrives at each one, which is then preserved in the resulting reflections. So now we're sending back a bunch of phase shifted copies, which are then going to interfere based on their phase differences, further diminishing that energy density of the reflection and helping us diffuse sound even more. So another type of diffuser you might be familiar with is a skyline diffuser, named for the way that when you look at this, it looks like looking down on top of a city or something. It actually looks pretty cool. These types of diffusers use the same principle, right? Each of the buildings of the skyline is of varying height, right? So they are of different distances away from the source material. They're going to take advantage of that same phase shift effect because they're sending back different copies with different phases. With the skyline diffuser, we also get a bunch of corners, right? Because the differing heights of the buildings exposes a lot of hard corners. And we saw earlier that those type of reflections are very useful for diffusing sound energy. So again, like I mentioned earlier, diffusion differs from absorption in this one key fact that it does not remove energy. It only displaces it and spreads it out over a larger volume of air or water if you're using diffusion treatment underwater. Using diffusion treatment is a great option for keeping a room sounding live and harmonic, but reducing the directionality and harshness of reflective distortions and artifacts. To demonstrate this idea, imagine a light fixture with and without a glass bulb covering the light filament. The light from the filament, just unfiltered at all, is very dense and harsh, right? It's very just directional and it just goes right at one spot and it's hard to look at. It doesn't spread out over a large space on its own and it's not very useful for lighting a room, right? The proper use case of this light fixture. But when we take that same filament and enclose it in the glass bulb, the light that we get is spread out over a much larger area and it's a lot easier to look at. It's much more useful for our intended purpose. The key here is that the total amount of energy being put out by the filament is the same whether the glass bulb is there or not. But using the glass bulb helps us get to our desired end without having to change the properties of the filament itself. You can think of sonic diffusion in the exact same way. Imagine a drum room where you want to have a nice live harmonic sounding room, but you don't want super intense echoes that you can tell, oh, that echo came from that wall, right? You don't want to hear that in your recording. So instead of just trying to absorb all of that energy and make the room dead completely, you can use diffusion treatment, just like we use the glass bulb. We take the same amount of energy and just displace it over a larger area to keep the energy we need, but use it in a more effective way. So at this point, you might be wondering, why do we even care about diffusion treatment if absorption can just absorb all the energy and just remove everything? Wouldn't it be easier for us to just make a room completely dead and then worry about building up from there? So in the Scitone episode on reflections and absorption, we learned that absorbers don't absorb sound uniformly, right? Their absorption is frequency dependent, and it's not perfect. It's not going to absorb everything and all the energy that we need. So this imperfect absorption is going to send reflections back to us that are distorted, right? If something only absorbs high frequencies well, or mid frequencies, then those reflections are going to still be in balance with low frequency harmonics and other content. If we use this type of imperfect absorption everywhere to try and just absorb all the energy we can, what we're left with is a room that sounds dead except for some weird unnatural harmonics left over from our imperfect absorbers. This is a worse situation than no treatment at all, because nothing is going to really sound natural or regular in that space. To avoid this situation, we need to use diffusion in harmony and in concert with absorption treatment. Absorption is going to remove some energy from the room, while diffusion is going to help the energy that's left over be spread and more usable and aesthetically pleasing. Really, it's about finding the right level of ambient reflective energy for your room, which is tuned with absorption, and then spreading that energy that's left and using it in the best way possible with diffusion. All right, friends, that is all for today's episode of Scitone. Thank you all so much for checking this out. I hope you enjoyed it, and I hope you learned a little bit about why diffusion matters, what diffusion is, and maybe what you can do to improve the diffusion of your space. This is the third episode in like a series I'm doing on room acoustics, where the first one was about reflections, the second one was about absorption and attenuation. This episode you just watched is about diffusion, and the next episode is going to kind of tie all those together with a final episode on reverberation and normal modes. Very, very cool stuff, and I'm sure everybody will be interested in checking that out. So yeah, look forward to that one. If you enjoyed this video, please like and subscribe. I would really appreciate that. And if you've got questions or comments on anything I talked about in this video, let me know. Let's talk about it. I'm a nerd, as you can tell, because I took the time to make all these science videos, so I obviously love to talk about science. So yeah, let's talk about it. Thanks again, everybody, and I will see you in the next video. Peace.